My name's Neil Hodgson. I'm the head of geosciences at Spectrum, and I'd like to share with you today some observations that we made in 2018 about how looking at regional seismic data helps us to chase some of the major plays around the planet, and how it helps us find new plays and go explore areas that perhaps we've never thought of before by looking at modern seismic data. This is some work that was done with my colleague Karina Rodriguez. She couldn't be with us for this recording, but what we'd like to do is take you through the giant regional play fairways that we see around the world, the ones that are breaking, the ones that are really happening, and show you how regional seismic data is helping us to understand these play fairways and helping you to prosecute them and explore them. So I'm going to start with what seems like a bit of a trite statement, really. Giant play fairways are play fairways for giants. And what I mean by that is not giants in the sense of the super major oil companies. It's not just big companies exploring in these play fairways, but it's giants in terms of people with giant hearts, courage, that can chase down a play fairway, chase their ideas down and find the new play fairways and the new oil and the new super basins that will lead us through into the next century of hydrocarbon exploration. We're going to start with Gabon. We're going to then look at some deep water turbidite plays around the world. We'll look particularly in Brazil's northern margins. We'll also compare that to Somalia, and we'll look at a basin that's basically never been seen before, and then finish off with Brazil's Santos Basin by looking where regional seismic data is helping us to understand where to go, where to find the next super basins. Now, it's a comment that I hear quite a lot is that the only place that we can go on Earth today to find new super basins is in ultra deep water, because these areas are largely unexplored. And whilst it's true that these deeper basins are actually largely unexplored, it's actually not the only place to find new super basins, and I'll explain this. So actually we're looking at a map here, a sediment thickness map produced by NOAA, and I've cut it off at the point of 3,000 meters water depth, so that the blue areas surrounding the continents there on their passive margins are where the water depth is less than 3,000 meters. That's important because in oil exploration, the deepest that we've drilled so far is 3,400 meters of water. So the areas that are marked in blue there are the areas where we've looked before for hydrocarbons, the areas where we've been able to explore and drill wells. Beyond that, though, there are some enormous sediment thicknesses where we've got more than 5 or 6 kilometers of sediment sitting over potential source rocks out in deep water. And when we can explore in these deep water domains, these are where we will find billions of barrels of oil in the future. And I'm going to come on and show you some of this as we go through the talk. But it's not where we start, because this comment, the only place to go for new exploration of any magnitude is in ultra deep water, is, I'm sorry to say, it's fake news. It's not true. And I'm going to start off with an example which comes from Gabon in West Africa. Now, on the seismic line that you can see on the left there, this seismic is not rubbish seismic data. It's acquired in 2006, and what we can see is the area where that green blob is there, which is the area where the hydrocarbons were discovered in a well that was drilled. That's in the syn-rift section of the southern part of Gabon. It's below the salt in the clastic syn-rift dentale formation. Now, this seismic was acquired 20 years after that well was drilled, and it's 3D data, and we can still virtually see nothing in the syn-rift. We had no idea how it worked. We got no real good concept of how trapping systems might be present, how many might be present, and how they might work in that syn-rift section. And yet, look on modern data. This was some seismic data that we acquired in 2017. It's on the lower of the black areas on the map on the right-hand side here. It's 11,000 square kilometers of 3D data. And it's almost exactly the same section, and you can see the reflectivity in the syn-rift. But it's not quite like syn-rift should have looked like. Syn-rift should have perhaps looked like a whole series of tilted fault blocks. And we can see these fold structures, which are actually antithetic rollover structures. So because we can now image into the syn-rift, which we just couldn't before, we can understand that there's a different sort of geology going on in the syn-rift, a different sort of trapping style. And as we look around the area, we see more and more of these structures in the syn-rift. All of the structures that you can see below the salt on this particular line, you could not have seen on older legacy data. So we've gone back to an old area, an area which had been explored for perhaps 60 years. And we've gone back to that area, and by acquiring new data, we've revealed a whole series of structures. On this one line, there's 4 different structures there, each of which has the potential for 100 million barrels. In the whole area, there are perhaps 100 structures like this. And we've gone back to this area, shot new data, and we've seen a whole play fairway that was just not apparent before. This is extraordinary. Or is it? No, I think we can do this on any passive margin just about anywhere in the world, where we think we know what's going on in the geology, acquire new data, and all of a sudden we realize, well, we didn't really know it, we didn't really understand it before, and now we can see the geology, we can explore it more efficiently and find the reserves that were not found before. And I think that this can be done all over the world in relatively mature areas by using modern seismic technology. Now, the most important leap forward in exploration in the last 30 years really has not really been a geological innovation. It's been a geophysical innovations, and innovations in processing is largely responsible for that. And so what we're seeing here is that we're deghosting the data. We're taking noise and multiples out of the data and seeing geology we never saw before, which is quite extraordinary for South Gabon, but I think we can do this all over the planet. Let's just look at the other play though. Let's look back at the deep water play, because the reason that below 3,000 meters of water depth hasn't been explored was largely due to drilling technology. It's only recently that we've been able to drill commercial hydrocarbon exploration wells in that sort of water depth. And the problem with doing this in 2014 was that to hire a rig that was capable of drilling in those sort of water depths would cost you perhaps $600,000 to $1 million a day. The advantage of doing it in 2018 and 2019, as it is the day I'm recording this, the advantage is that we can do it for $200,000 to $300,000 a day. It's half as expensive to drill in deep water than it was in 2014. The last 4 years of suppressed oil price has meant there's fewer rigs available in the market. There was less exploration in that sort of water depth, and that meant the day rate came down. All of a sudden, deep water is the place to be. And in fact, it was only after a period of low oil price that deep water exploration really becomes commercial and really becomes exciting. So we're going to have a look at the possibilities for doing this around the world now. This graph here has on the y-axis the water depth, which is the depth that we're drilling in, against time on the x-axis. And since 1960, when we really started going offshore into the world's ocean, we've made a steady progress into deeper and deeper water. Currently, the deepest water well was the Rea 1 well drilled offshore Uruguay. And this was drilled in 3,400 meters of water, but that's the end of a long period of development of drilling technology and equipment that will take us out into that sort of water depth. And you might think, well, I'm afraid, drilling that sort of water depth can only happen when oil prices are high. Well, on that graph, the curve of the incremental records in setting water depth drilling, I've emboldened the part of that curve where the oil price was below $50 a barrel. So this is low oil price areas. And you can see that a lot of the majority of the main step changes in our ability to drill in deeper water happened when oil prices were low. And that's absolutely crucial, because now we're not in an environment where oil is $120, $150 a barrel. We're in an environment where oil is perhaps half that. And it's still sufficient to encourage us to push out into deep water. Cost of drilling is cheaper, and the cost of innovation is that if you don't innovate, if you don't get out to deep water, you will miss the discoveries of the future, the giant fields that we're going to find in the future. Where are we going to find them? Let me show you an example here. This is a seismic line from Uruguay where the Rea 1 well was drilled. And the Rea 1 well drilled more or less in the center of that seismic line, drilled down to that bright event. It's actually in the tertiary, a bright event that was targeted by Total at the time. Well, it was an unsuccessful well. That was just the bright event. It's just a 5% gas will generate that sort of seismic response, and the flat spot that was on the seismic wasn't a hydrocarbon water contact, it's actually a lithological contact. But what lies underneath Rea 1 is extraordinary. Beneath that tertiary target is a whole Cretaceous section, and it's full of contourite affected turbidite basin floor fans. And I'm going to come on and talk about mixed systems next, because the big innovation in geological understanding for deep water exploration over the last 5 or 6 years has come in our appreciation of how important contourite and mixed systems, mixed contourite and turbidite systems together are to exploration in the deep water. And if you see below the speckledy, brighter events in the Cretaceous there's a very bland event above the basement. It's almost like it's washed out. It's low frequency, it's not very high acoustic impedance contrast. That event there is actually the source rock. So we have an Aptian source rock, and I'll show you some evidence for that in a little while. An Aptian source rock sitting just underneath a whole pile of clastics that were not tested by Rea 1. And in fact, you can go all the way from Cape Horn and Tierra del Fuego in the far south, all the way up to the Santos Basin, and there's not one well that tests that Cretaceous section where we might think that there might be a play. It's such an exciting, unexplored play. And in fact, on this particular line, one of the biggest prospects in the world, which closes in an area that is, as long as Uruguay is, in that whole margin. It's one of the biggest prospects in the world, sits underneath Rea 1, but was not tested by the well. One thing you can see on this seismic line, on the left-hand side of your screen, as you go up dip, is you can see a lot of bright reflectors. These are in a huge contourite drift. It's a plastered contourite drift that is perhaps as much as 3 kilometers high. And contourites have become the big hot topic in deep water exploration. Run across the slope, and they take the fines, they take the mudstones and the silts, and they go and build large contourite drifts with those silts. And what they leave behind is the fine coarse clastics, the high quality coarse clastics that we're looking for when we're exploring for oil and gas in reservoirs. The example that we've got here on the left is from Rovuma, where these have been drilled, and the yellow areas there are the very high net to gross coarse clastics, perfect reservoirs for oil and gas, and the green section there are all the fines that came out of the turbidites and they've been built into turbidites. And these turbidite currents actually push the constraining channels for the turbidites. They push them around, and they're quite characteristic on margins. You can see this is a good example of a migrating channel system through time. We see more of these. This example here is not in Rovuma like the last example, but here we're in Argentina, and we're seeing the same thing, a migrating channel system with time being pushed by contourites. And what that means is that the bright event that you can see about halfway down that seismic line, that bright event there, high acoustic impedance contrast, is sandstone. It's very coarse sandstone, and it's going to be very high quality reservoir. So if you can find that in a trap, and you find some indication we've got hydrocarbons from the seismic, then this would make a fantastic target for exploration. This is where we're going to find the big reserves in the future. You can see the model that we've got on the left-hand side, which is a classic basin floor fan coming from a constrained channel which comes again off the slope. And these fans are, I mean, it's the same model, but what's happening here is that they're being affected by contourite currents running parallel to the coast, running parallel to the contours, and it's just improving the quality of the sands. Another really cute thing you can see from this data, I mean, we used to look at these regional lines on the margins on time sections, PSTM sections, time sections. And what we didn't really perceive was that when you look at that same section in depth, actually as you go offshore, the geometry is it's up dip as you go outboard. And the reason for that is that they're sitting on oceanic crust, which is older and colder towards the shelf and towards the shore, so that's suppressing it, pushing it down, and it's younger and warmer as we go outboard, which is lifting it up. And that creates a trapping geometry for a stratigraphic play that you know must work, because otherwise these sands would have to stretch all the way from Uruguay in this case to Namibia, which they clearly don't. So you know that that strat trap works, and you can also see that underneath the coarse clastics here we've got a very different sort of unit, and that unit is a source rock. It's the Aptian source rock. So Aptian source rock charging clastics that are dipping up dip as you go away from the coast. Here's another example of the same phenomenon from across the pond. This is offshore Senegal and The Gambia. And again, as you go offshore, so that the dipping geometry is rising up as you go offshore. And on this particular line, you can see where turbidites that are coming off the shelf down onto the basin floor will have a trapping geometry that rises up as we go out towards the west in this particular case. Now, very little was known about this margin until Cosmos started drilling on Tortue and then Teranga, and then lastly out to Yakar, and finding huge amounts of sand in basin floor settings. These sands have been affected by contourite, so they are in giant sand waves of beautiful reservoirs, clean reservoirs, and they have hydrocarbons in a trapping geometry that you can see on example on this line here, and that extends all the way up the margin. Now, getting to the basin floor fans where the sands are not on the shelf, they're not on the slope, and we've done a lot of drilling on the slope around the coast of West Africa, not always terribly successfully. But getting down into the basin floor where we have these trapping geometries, it's often quite hard to do because it's in water depths of more than 4 kilometers. Now, in 10 years' time, we'll be able to drill in more than 4 kilometers. Just currently, it's kind of difficult. But there are places on the planet where you can drill in just 3 kilometers of water and reach these basin floor fans. And that's where the convection in the mantle is lifting the oceanic crust up and basically lifting your basin floor fans into a drillable water depth. Northwest margin of Africa is one such example, but on the little inset here is a dynamic topography map produced by Hogarth et al., Nicky White's group in Cambridge. And this is a map of where the oceanic crust is higher red or lower blue than it should be. All those red areas on those maps, on that map, is where you can reach basin floor fans in less than 3 kilometers of water. So these are the really hot areas for exploration moving forward. Taking this example here from the Gambia, the very thick pile of sediment there has right at the base of it a Jurassic section, and in that Jurassic section there's a source rock. One thing that we can do with our big regional seismic lines is create a conjugate arrangement, and so I'm going to show you a conjugate mishmash between the line from Senegal, which is on the right hand side, and a line from the east coast of the US. And what I've done here is I've married those two seismic lines up at the same scale, just where they both have oceanic crust, which is about 150 kilometers offshore North Senegal and about 280 kilometers offshore east coast of the US. And that allows us to take the source rock that we can infer from the Jurassic on the west coast of Africa and push that through to the east coast of the USA. Now, it's quite extraordinary to me that one of the least explored places of the planet, which has patently a very exciting margin for deep water exploration, is the east coast of the US. I think its time will come, it's not there yet, There's currently a moratorium on drilling on that margin. But what potential lies there? All of the plays, Tortue, Yakar, the SNE equivalent, they're all present on the east coast of the US, such as we see on the conjugate margins in West Africa. Now, one of the things I'd done to that previous line to marry up the oceanic crust was that I'd made an adjustment for dynamic topography. So that's what we're going to see on lining up these two seismic sections from Namibia and Uruguay. And here I've taken the source rock that's proven in Namibia and I've driven that through into Uruguay. But in order to do that, I've had to suppress the Namibian line by perhaps 2.5 kilometers in order to get the oceanic crust, exactly the same age oceanic crust, because it's the conjugate margins, to get it at the same point. And that is the effect of dynamic topography, the effect that's quite visible before our eyes of the mantle convection, either pulling oceanic crust down or lifting it up. When it's lifted up, you can hit the basin floor fans in relatively shallow water, and it's harder to do that where it's been suppressed down.